Things hooked up. I'll take attendance. I'll take attendance after the first break. Okay, this organic lab. On the website, you already have access to the first few folders on here, the safety documents, the syllabus, instructors and references, our rubrics, and then down to introduction to the chemical literature, and then the chemicals and the safety data sheet links for the chemicals that we're going to be doing for experiments. We're not going to be doing experiments the first 4 weeks. We're going to be doing lectures on spectroscopy. And so today's the first one of 4. So when we get closer to the experiments, then we will I will talk about those. So in terms of going over the syllabus, you can go ahead and read that. It's going to be very similar to what you had last semester. And if you had organic somewhere else, or not last semester, which I don't necessarily see anybody that would fall into that category, then you can come and see me, but I don't see anybody there that's there. So let's start with, so what I'm going to do is I'm going to kind of start here with the idea of what is spectroscopy? What have we not talked about in organic lecture to this point? I will say that in terms of the lecture book material for what we're going to talk about for the next 4 weeks, if you have Dr. Kwan, it'll be in the Wade textbook. It'll be in the Top Hat textbook. In Wade, I believe it's chapters 14 and 15, or 15 and 16, one of those two. And then in the Top Hat, I think it's 15 and 16 or 16 and 17. Anyway, there's IR and NMR spectroscopy. And so what we're going to talk about is, today we're going to talk about infrared spectroscopy, and we're also going to talk about setting all of this up, and then we're going to talk about mass spectrometry. Now, and we're not going to go to 5 every day. That's just not happening. But probably till 4-ish, maybe after that, depending. And so we're going to break that up with problems and questions so that you're not just, you're not bouncing your head off the table. All right. There's a lot of ways to do this. I don't think there's a good way, at least we haven't found it yet, to talk about spectroscopy. We could incorporate it in a lecture, but then we're going to go at an even faster pace than we already are, if we have to include all this stuff there. So we've been doing it in the lab. Okay, the reading assignment here, I believe, is for Wade, but again, you can take that from the Top Hat. It's another chapter. So, all right, what is organic spectroscopy? Organic spectroscopy is a way to determine the structures of molecules, and also we're going to determine purities of organic molecules. So that is the important aspect of this. Let's see, I don't think this one has a laser pointer. No. All right. And I don't have Dr. Chai's big stick. Okay. So we've learned some reactions on how in organic lecture. We've talked about, for instance, like the state set rule or Markovnikov competition. And the real question is, if I take any alkene and I add HBr to it, how do I know I get the Markovnikov product and not the anti-Markovnikov product? Well, I have to determine the structure of the molecule. And that was a lot more difficult when you didn't have instrumental techniques to determine the structure of the molecule. Nowadays, with the instruments that we're going to talk about, infrared, nuclear magnetic resonance, which is NMR, and mass spectrometry, I can basically determine the structure of something that somebody just walks up to me and gives me off the street. They walk up to me, hey, here's a white powder, can you tell me what it is? And I probably can, using those different techniques. Before, it was very, very difficult. And I'll just give you an example of that. So let's imagine that you think you have a double bond in your molecule. So you can do the color test, which is a qualitative test, and you can say, okay, if I've got a double bond in there, if I add bromine liquid to it, it's going to immediately react, and bromine is orange, so if I add a drop of bromine liquid, the orange color is going to immediately disappear. And that would tell me I have a double bond. It would also tell me that I might have a triple bond. If I let it sit too long, it's going to do free radical halogenation, and the orange color is going to disappear. I might say, well, let's use KMnO4, the nice purple color solution. KMnO4 will react with a double bond, either to add two OH groups, cis, or it'll cleave the double bond, but either way, the purple color will disappear, and the product of that is MnO2, which is a brown precipitate. So people came up with all these different color tests that you could do. Or if you had an alcohol, you might say, I think I have an alcohol. Let me drop a very tiny piece of sodium metal into it. And if it fizzes, because it's producing H2, then I've got an alcohol. If you drop a very small piece of sodium metal in the water, it also fizzes before it explodes. Right? Alcohols are going to react slower, and we'll get to that reaction this semester. So we had all these color tests. I will just tell you, this is going to sound like a story, everybody went to school in the old days walking uphill, both ways in bare feet, 10 feet of snow. But when I took the second semester of organic lab in the middle 80s, they gave us 4 compounds in test tubes and said, figure out what they are. And that was half of the semester. And it wasn't just 4 hours a week. It was any time that you could get in the lab, go ask the secretary, she'll open it up for you. You'd go in and keep working on these things. And I don't know. I think I probably got a couple of them. But it was really difficult because we didn't have the array of spectroscopy that we had now. Or at least if we did, we weren't able to use it. So we're going to talk about how do you determine the structure of the molecule from scratch. How do you determine whether you made the molecule you think you made in lab? How do you know it's pure? Right, because so far we haven't done anything really with percentages outside of GC. Right, melting point doesn't give you purity. Right, in your lab report you said, well, I think it's kind of pure because the melting point is actually. But now we can get some analytical data and say, oh, it's 90% pure. But we can also determine what the impurity makes and what the side products are. So that's what we're going to do with spectroscopy. And the question is, what techniques, and then we're going to talk about the techniques and also the how you use them. So here is an incredibly complicated molecule called Taxol. Taxol is now routinely used for to treat ovarian cancer and probably a number of others. It's got a lot of chiral centers. It's got rings bigger than 6. It has a lot of different functional groups. And so this drug actually originally came from the bark of a California yew tree that grows in Oregon. And at the time, the NIH, the National Institutes of Health, had a program where people were trying to isolate and identify as many anti-tumor compounds as they could. And so they were getting the anti-tumor compounds from everything. Barks of trees, they go out scuba diving, get some like a little sea urchin from the coral. Unfortunately for that sea urchin, it had to sacrifice itself Well, it didn't sacrifice itself. It went into the blender. It couldn't reach around to turn the blender on. And so you blended up the sea urchin, and then you took and see whether that mixture has anti-tumor activity. And if it did, then you had to slowly begin to separate compound after compound after compound to find the right one. So Taxol came from the bark of the California yew tree. It's like a little scrubby tree that grows in Oregon. And they found that extract had anti-tumor activity, and that they needed to find out what the exact compound was. And this is back probably when I just started teaching, like mid 20 years ago. It was just out in clinical trials. But if I have this compound, I need to know what its structure is, because there's not enough bark in enough California yew trees to treat all the people with cancer. So we need to be able to synthesize it. But before I synthesize it, I need to know what its structure is. Now, this was determined by a technique called X-ray crystallography, and I'm only going to show you this. This is not one of the techniques we're going to learn about, but this is an exact technique that you can, if you can grow a little tiny crystal of the molecule, a perfect crystal, you can get the structure exactly, including, if you're good at this, the exact R&S configurations of the molecules. So what happens in X-ray crystallography, just to give you kind of an idea, is you got to grow a crystal. So if that crystal at the top didn't have that small bite out of it in the corner, it would be perfect. Perfect shape, you can see through it. The one at the bottom I just don't think is in focus, but it's a little bit bigger. These are millimeter crystals. Okay. Now in your biology textbooks, you see things like the structure of DNA, RNAs, enzymes. You either see the exact atoms or you see those little cartoons with those little arrow things, the beta helices or the sheets. Those all come from X-ray crystal structures. So this technique is used a lot in biochemistry and molecular biology, as well as just small molecule crystallography. So if you can grow that crystal to be perfect, and last semester we didn't grow any crystals like that, right? We got some sheets, some plates, but we didn't grow anything like that. And it wasn't that we didn't try. If we tried, we probably could. So if you can get a little crystal of it, which they were able to do for Taxol, you take an X-ray beam and you pass it through the crystal, and the X-ray beam diffracts into all these different beams. And then it's just pure math and computers that take the intensity of each one of those beams along with its orientation and reconstruct the molecule and reconstruct the structure so that you end up with a structure like I'll show you in a moment. So this is a really old instrument. This is the one that we used when I did 2 years of a postdoc in X-ray crystallography, which is why I like this. I couldn't do it now because the techniques have gone way past me. But if I do get something with a small crystal, or my intent is to grow a small crystal, I'll send it. Now I guess I have to send it to Purdue because that's where my guy is. So I send it to him, and then he determines the structure. He was at Youngstown State up until recently. So we collaborated on papers and stuff. So at the end of this, there's a small fiber, sort of like a melting point capillary. That's where you put your little tiny crystal. And then that instrument does the analysis. So you can kind of see that's where the crystal would go. On the right, that's where the beam of the X-ray comes out. And so you get a structure like this. And this is these purples are lithium plus cations. These are O minuses. So this is actually what we'll later on learn. This is an enolate of a ketone. It's an anion with a lithium counterion, and it makes this like barrel-shaped, what's called a hexamer. But you can see That looks like a benzene ring. This is sp hybridized, so there's a double bond there. So you can determine the structure of that, and you can determine the structure of any of these molecules that you can get to grow as a really high quality crystal. And so what you have to think about is what is a crystal? And my example is, let's say we take a molecular model and we put it in a shoebox. We might be able to put 2 molecules in a shoebox. Then you take shoeboxes that contain those molecules in exactly the same positions and you stack them in 3 dimensions. That's what makes a crystal. So that you're actually only determining the structure of 1 molecule in a box. And then you can generate it from there, like that. And this only came about, I think, in my 2nd year as a postdoc because we didn't have the computer capacity to actually look at these big structures. And you have more power in your phone probably now than I had on that computer. So this has gone a long way. You go to biology and your biomolecules, you can now see the 3 dimensions. You can see the 3-dimensional structure because somebody grew a little tiny crystal of, for instance, DNA. Right? That was Watson and Crick and Rosalind Franklin that they did all that. And and if you want to read an interesting story, that's how they came about that and her role in it. And she could have scooped them both, except I think she made one assumption that wasn't quite correct. But there's all that's a interesting story. There was, now we see these forever. But that came from a little tiny crystal of DNA.
Are certain molecular structures not able to form crystals?
Well, that's the thing. In order to do this, you have to form a perfect crystal. And so not only do you have to have a good shape and have it clear, but there also can't be what's called twinning, which means that like 2 shoe boxes aren't end to end. They're kind of like stuck in a different way. And there were ways the old timers used to get around that. But I think the last crystal I sent out, he sent me a partial crystal structure coming back, so I knew what it was. And he said, this is a twinning that only one group in the world can deal with. So I didn't bother sending it to them because I figured they had enough problems. They didn't need mine. But then what you do is you just keep growing it over and over again until you get it perfect. So this is the problem. Not everything we made in lab was a solid, let alone getting it to be a perfect solid. So you hear about, we put these things on the space shuttle to try and grow perfect crystals in 0 with gravity. Or now the Chinese might be doing that because they landed a thing on the dark side of the moon where nobody can see what's going on. So I think they're trying to grow plants. They're trying to grow like soybeans and stuff there. I thought, oh, cool, they just threw it out on the surface and they're growing. Now they're in little containers that are held at 25 degrees and they have oxygen and everything. So this is part of the space with the space laboratories where, we can maybe grow crystals of biomolecules and that'll help medicine. And I don't know how well it's panned out, but it's a good idea. So all the structures that you see in your biology, your microbiology, your genetics books, those came about from crystallography. But the problem is we can't get everything as a perfect crystal. And so what do? Then we have to use some complementary techniques to try and determine the structure. And by complementary, what I mean is one technique will give you certain aspects of the molecule, and the other technique will give you even more information. So you have to use all of them together. If it's a brand new molecule that's never been made before, you got a lot of work to do. If it's something that's been made before, some of these techniques will compare that spectrum to the known spectrum and give you matches. But if it's brand new, it's not in anybody's database. So that's what we use, and we can go anywhere from 10 to 100 milligrams. Sometimes this can be in the nanogram region, which we'll talk about with mass spec later. When you have a drug test taken, they're using mass spec and they're looking for metabolites in like your urine, and those metabolites are at super low concentrations. So we can, the more stuff we have in general, the better, but if we have really tiny amounts, we could still do it with certain techniques. So here are the four. Ultraviolet spectroscopy, I don't know that we're going to talk about, but ultraviolet spectroscopy or visible spectroscopy is what you did in general chemistry whenever you measured the absorbance of a solution that has a color to it. Because that molecule, in order for it to show, for it to transmit visible light, has to absorb visible light. And today we're going to talk about infrared, which we use to identify the functional group in the molecule. And then mass spectrometry, which can give us the molecular weight and give us the pieces of the molecule. And then finally, NMR, which is one we're going to spend the most time on because that gives us the carbon-hydrogen skeleton of the molecule. So we can determine the difference between methyl, ethyl, isopropyl, propyl, isobutyl, butyl, tertibutyl. We can tell the differences in all those functional groups using NMR. And so that's the most, in my opinion, that's the most powerful one, but that's because I've been doing NMR for a long time. And if I was a mass spectrometry person, I would tell you that mass spectrometry is the way to go. But those two are very, very, very powerful. Okay. All of these are based on electromagnetic radiation. All except mass spectrometry. So what is the electromagnetic radiation? Well, remember that there's all these types from, I don't know, general chemistry, physics. You've got high energy like gamma rays and X-rays, down to things that are pretty innocuous like radio waves. What's different about all these? Either their the wavelength, and of course if you take the equation E equals h nu, where nu is frequency, of course you got a longer wavelength, you've got a shorter frequency and vice versa, or shorter wavelength is a higher frequency. When you convert that frequency value to energy, every one of those has a higher energy. So X-rays is going to go right through us. Radio waves, kind of, but X-rays are more damaging. So we're going to use these. We're going to use infrared, and we're going to use radio waves for NMR, for nuclear magnetic resonance. Okay. So how does this work? Well, here's how it works. We take, for a molecule, just like an atom, there's an excited state, there's a ground state. So in the ground state, what happens is we absorb energy to have the molecule go up to the excited state. And so there is an absorption of energy. Now, because the excited state, ground state energies are basically exact values, there is an exact delta E for that transition. And so that means if our excited and ground state energies are slightly different, there will be a slightly different energy of light that will cause this to happen. And so if there's a difference in energy, remember energy equals h nu, where nu is the frequency. And so that if that energy is different, the frequency of light that causes that transition is different. And if the frequency of light is different, that means that we can see a difference between those different frequencies or those different wavelengths. So using light, and you know that we can that we can separate light into its wavelengths using either prisms or, if you ever have a CD, I don't even know, or CD's passe now. But if you had a CD and you held up to the light, you see the rainbow effect. The grating, the CD is acting like a grating, and so it's separating the different wavelengths of light. So we actually use kind of both in instruments. We might use prisms or we might use gratings to bring in white light and then change it into all of its different frequencies, or separate it into its frequencies or wavelengths. And obviously, if we have a laser, the laser is one particular frequency. So that's how we're going to use light to sort of interrogate the molecule, because we can change the frequency of light very precisely. And these energy differences are very precise. So you want to make a spectrometer? Here's what you do. Get yourself a light source. Get a prism to separate the light into its wavelengths. And then when the prism is separating the wavelengths of light, rotate the prism so that the sample, one by one, each wavelength of light goes through the sample. Get a detector and measure how much light makes it through the sample. And so what we're going to do that's different than what you do in general chemistry. So in general chemistry you do this, but you're measuring the intensity of the light that you're changing over to absorbance. What we're going to do is we're going to actually measure the intensity or the absorbance of the sample and plot it according to the frequency. So we're going to make a spectrum out of that. And so the spectrum is going to look something like this. We're going to scan through the different wavelengths, and then where the molecule absorbs that particular frequency, we're going to see a peak. Okay? So what we're going to work with is the spectrum. What you worked with in general chemistry, or analytical if you did any visible spectrometry in analytical, what you did was you dealt with the intensity of the light at one particular wavelength, right? Because you prepare a Beer's law plot where you plot concentration versus intensity and you get a straight line. But what we're going to do is we're going to use the spectrum to get information about the molecule structure. So that's where we're going to do things a little bit differently. Okay, so that's kind of the basics here of using light, to look at molecules. It's all based on that ground state, excited state transition. Okay, so everybody kind of with me? Infrared spectroscopy. So, what we're going to do with the infrared spectroscopy is we're going to determine the functional group of the molecule. Now, where is infrared radiation? Infrared radiation has a wavelength of light that goes from 2.5 times 10 to the minus third, 2.5 times 10 to the minus 4 centimeters. Organic chemistry is weird, at least in terms of instruments from the standpoint, and particularly from infrared, because when it was developed, they didn't use proper conventions. One of the things we're going to see is peaks don't go straight up, the peaks are upside down. So the baseline is going to be at the top of the spectrum, and you're going to see peaks that come down. That's not normal, right? Normally we see peaks straight up. The other thing is centimeters. When we measure the wavelength of light, we always use nanometers, except in organic chemistry because we use centimeters. There are people that use microns, but we're not going to do that because the plots look completely different. And so the best ones are in centimeters. So that's a little bit different because in general chem you would have talked about measuring the absorbance at maybe like 400 nanometers or something like that. And we don't even actually use the centimeters What we do is to make these large numbers, because the wave number in centimeters is going to be really small. What we do is we form this thing called the wave number. And the wave number means we take 1 over the wavelength to get reciprocal centimeters. So it's bad enough we're not using nanometers and we're not using centimeters, but we're using 1 over centimeters to make our plots. But what's important is that the scale will be the same for all the molecules. So that's where infrared radiation is. You feel infrared when you walk out when there's actually sun out there, right? You walk out into the sun, you get warmed up, that's the infrared radiation. If you want to keep food warm, you can put an infrared, bulb above it, and that'll keep the food warm. You get out of the shower at some hotels, they have an infrared light above, I guess to give you that luxurious feeling of, getting warmed up. And why you get warmed up, give me a few minutes and we'll talk about that. So that is where the infrared radiation is. So how do molecules absorb infrared radiation? I have some video diagram. I have some sort of videos of this on a thumb drive sitting on my office desktop. So I will, at the first break, go and get them. But the way infrared radiation works is that the wavelength of the light is exactly the same as what are called molecular vibrations. So here we see springs. And that's the way molecules are typically represented when we talk about infrareds. So let's say I've got 2 hydrogen atoms, or 2 oxygen atoms, or any 2 atoms, HCl. They're going to be vibrating back and forth. And the frequency at which they vibrate is in the infrared region. So when they vibrate, they have a particular frequency. When you pass the infrared radiation of that exact same frequency in the molecule, it absorbs the energy. They vibrate a little bit farther out, but at the same frequency, you go from ground state to excited state. So the frequencies have to match up. And so that's a simple vibration, a simple bond stretching. HCl is going to be different than HBr. In the PChem lab, they actually look at the HCl stretch of the chlorine 35 isotope versus a chlorine 37 isotope. Because when the masses are different, it's like putting a heavier mass on the spring, the vibrations are going to be slightly different. And the beauty about light is that we can actually resolve light down to very precisely. We can get down to a nanometer. So we can tell the difference in even the slightest variations on that frequency. So the vibrational frequencies then are in infrared. And so that's the key in terms of us using infrared to tell us about functional groups. What we're going to find is on some particular parts of the spectrum, that's where you find the OH stretches. In another part of the spectrum, that's where you find the C double bond to O stretches. Oh, I can tell now if my molecule has a carbonyl or an OH. A hydrogen attached to a double bonded carbon is going to have a slightly different stretch than if that carbon was sp3 hybridized and part of an alkane. So we can tell the difference between these different functional groups by where they are on the spectrum, by those different frequencies. And that's what we're going to use infrared for. And the only caveat to this is that for infrared, for a molecule to absorb infrared radiation, it has to be polar. Because one of the quantum mechanical rules on all of this is that as the bond gets closer and farther away as it vibrates, the dipole moment changes. So when the atoms are closer together, you have a stronger dipole. When the atoms are farther apart, you have a slightly different dipole. Well, remember, the molecular dipole is what we use to figure out whether a molecule is polar or not. So you have to have a polar molecule. A nonpolar molecule doesn't necessarily show infrared. Like oxygen will not absorb infrared. Nitrogen will not absorb infrared. So it has to change its polarity. And so this infrared radiation absorption, right? We can go beyond chemistry. We can talk about, okay, why can we live on Earth? Why could we not live on the moon? Well, there's a number of reasons, but one is because we have this nice atmosphere, we have this nice warmth, right? The global warming. Well, we experience global warming because we can live. If there was no global warming in an absolute sense, we'd be like on Venus and dead, right? So there are gases that are absorbing infrared. They're trapping infrared from escaping. And so those molecules are polar. They're in our atmosphere. What kinds of gases are those? Right? Some of you are biology majors. You've been global warming, been hit over the head with 2x4s numerous times about its badness. CO2. What else? Methane. And the interesting thing about methane is it's non-polar, right? The way we classify it is the same with CO2, but the key thing is we're going to talk about stretches, and those stretches are actually not, there's a dipole when they stretch. So the molecule, when it says a polar bond is usually IR active, and a nonpolar in a symmetrical molecule will absorb weakly or not at all, it might absorb a little bit more strongly. So CO2, what else? Ozone. Ozone's a slightly different problem than global warming, but it is polar and would absorb a little bit of infrared. How about water? What's the most populous greenhouse gas in the atmosphere? It's water vapor. So the reason we have our nice climate here is because we've got a lot of water vapor. Water vapor is much more than CO2. Now the change in CO2 over time is what everybody's worried about. And it's measured on the top of some volcano in Hawaii is where the worldwide measurement's made for. But actually they make that measurement by basically taking a chamber and filling it with the air from that place, and then measuring how much CO2 is in the atmosphere using infrared. And so that's how they get that measurement of, I think we're up to 300 and some parts per million. Those of you that had Dr. Johansson's class last semester. So that's how they make that measurement, is because CO2 will actually absorb. It will absorb infrared, even though it is not a polar molecule. Its stretch has to change its dipole. So we'll get, as soon as I go to my office and get the video, or get the stick with the video, then I'll be able to show you. Otherwise, I've got to do things like this. I've got to say, okay, when CO2 stretches this way, its dipole moment doesn't change. Right, because these two are canceling each other out, so if they move at the same time, they're canceling each other out. But what if it moves like this? Then its dipole moment is changing and it is absorbing infrared radiation. This is the C, these are the two double bond O's, if you didn't figure that out. What if it's doing this? Then it's changing its dipole moment. because these two dipole moments are adding up to something this way when it's on the other side the other way. And if it does this, then it is changing its dipole moment. So of the four ways that it can vibrate, and vibrate also means bending, three of those absorb infrared, which is why CO2 absorbs infrared very strongly. Water, okay, same thing. Here's my water molecule. If it does this, it's still changing its dipole because when it pulls up, that dipole gets smaller, but when it gets larger, then it can do this. But I got a video that shows all those motions too. Otherwise, I have to stand here and do all those motions, which I have done before I had the nice animations. So the idea here is that molecules, whether they're stretching their bond or whether a CH3 group is going like this, they're changing their dipole moment, and that frequency then is in the infrared. And so a particular wavelength of light will cause that molecule to have energy absorbed. But each one of those vibrations is different. So it shows up on a different part of the spectrum. Okay? So I've just given you an infrared spectrometer. We just basically need infrared radiation. Where do we get that from? We get that from a glowing wire, probably like what's in a light bulb. Although those are going away, right? Our incandescent light bulbs, they're being replaced by something not incandescent. So there'll probably be a day when it's like the little wire inside of a light bulb, and there won't be any of those around. But that's what creates the infrared radiation. It also creates visible light, but we're only concerned about the infrared. And then you can use a motor with a mirror. Well, the mirror doesn't do that. It's the monochromator that changes the wavelength. So what we do is we come up with a plot. So that plot in blue, it's upside down. And it goes from about 4,000 wave numbers on the left down to about 400 on the right. And so that's what we plot. So when we see an upside down peak, that tells us, hey, this functional group is in that molecule. Okay. So that's what we need to look at in terms of the different functional groups. So we're going to go through alkanes, carbonyls, and look at the different functional groups that make up that each one of those stretches. You have these pictures, and again on the thing in my office I have these pictures where I can click and it'll animate what the vibration is, just to kind of reinforce that. So since that's not here with me, what we'll do is we'll take like a 5+ minute break, and then we'll finish up. Then we'll do the IR, and then I have some problems. You have the first set of. There's two. There's one that has a date on it, and one that says IR homework problem set. We're going to go ahead and we're going to match those compounds up to their different infrareds. But first, we'll learn about where each functional group shows up in the spectrum. All right. So we'll be back here at. How about we be back here at 2:05?